Hello my dear children of class 12 science. Today we do again continue with the chapter that we already started in the last class, that is atom, origin of spectra, the Bohr's theory of hydrogen atom. Now this is the first chapter under unit number 8 that we are dealing it. Okay, and in the last class, if you remember, we had done up to the topic called total energy of an electrons orbiting in an atom, in a nucleus, around the nucleus. Okay, now the expression that we had derived in the last class was E, the total energy of an electron, okay, is equals to minus m z square e to the power 4 divided by 8 epsilon naught square h square and n square. Now in the expression, m is the mass of the electron, z is the atomic number of the atom, okay, charge of electron, permittivity of free space, h, you know, it is called what constant? Planck's constant. And n is the number of orbit in which the electron can revolve. That means this relation, this particular relation which we have derived, it is the expression of energy of an electron in which orbit? Nth orbit. This is the total energy. This is the expression total energy. Okay, this is the expression total energy of and what electron? Orbiting electron. The orbiting electron means the electron which are revolving the orbit. For what orbit? This is for nth orbit. So this particular expression is for what orbit? Nth orbit. So nth orbit can be any orbit. It can be first orbit, it can be second orbit, it can be third orbit, any orbit. Okay. So this is a general expression to measure the total energy of an electron in nth orbit. But in this expression, if you see, there is a what sign? Minus sign. There is a what sign? Minus sign. Now this minus sign says that the total energy, so total energy of an electron orbiting around the nucleus of an atom is always what? Negative. Always what? Negative. Now what do you mean by this particular negative sign, and what this negative sign indicates? So it says that the electron is bound by the nucleus. Every electron is bound by the what? Nucleus. Now why? Because nucleus is a positive charge. As you know, nucleus is what charge? Positive charge. And electron, even if one electron is revolving, say in the first orbit, say, then this electron is a what charge? Negative charge. And between negative and positive charge, what happens? Attraction takes place. Okay, and this attraction exerted by a very strong force, electrostatic force. That means this negative sign means that the electron is bound to the nucleus. So energy must be supplied. So if electron is bound by the nucleus, then energy must be supplied to it for the ejection. For this what? Ejection. Means energy must be supplied to the atom to eject the what? Electron. To eject the what? Electron. Okay. That means this energy is maximum negative in the lowest orbit, because the electron in the lowest orbit is strongly bound by the nucleus. But when you calculate this total energy will be maximum negative at the what orbit? Lowest orbit. Which means that in the lowest orbit, the electron are tightly bound. Electron is what? Tightly bound. Okay, due to the strong force of attraction exerted by the nucleus to the electron in the lowest orbit. Okay, so you need a maximum energy, negative energy, to be supplied to the electrons. Okay, to eject from his orbit. Okay, that's why this minus sign indicate that the total energy of the electron is always what? Negative. Okay, now from this expression, we calculate the energy of an electron in any of the orbit. But along with that, we calculate the frequency of emitted radiation and the wavelength of emitted radiation. Frequency and the what? Wavelength of what radiation? Emitted radiation. Okay. Now in order to measure the frequency of emitted radiation and even the wavelength, corresponding wavelength of emitted radiation, one thing keep in mind, children, that as far as the Bohr's theory is concerned, the atom must be in what state? Excited state. That means there must be the energy which has to be supplied to the atom. And once the energy supplied to the atom, the electron definitely from a higher orbit from outer orbit goes to the higher orbit, and that electron cannot stay in the higher orbit, and that electron simply jump from higher orbit to which orbit? Lower orbit. And when electrons jump from any of the higher orbit to any of the lower orbit, then due to that there is an emission of radiation takes place. And this emission of radiation takes place in the form of electromagnetic radiation. Okay, electromagnetic what? Radiation. That means for the calculation of frequency and wavelength of emitted radiation, the atom must be in what state? Excited state. Okay. Now I consider that the atom is already in the which state? Excited state. So I write on in excited state of an what? Atom. The excited state of atom means the atom has already received energy from outside. Okay. So under this state, the electron jump from higher state, any of the higher energy state, to any of the lower energy state. So I consider that the electron, suppose electron, okay, jump from a higher state. Then that higher state I consider, say, N2, to a lower state, energy state, or the lower energy orbit, that is what? N1. Suppose consider the electron is in any of the higher orbit or state, N2, and is jumping to the lower, any of the lower energy state or orbit, that is N1. So under this case, what happened? Definitely the frequency of emitted radiation will emit, the energy will, there is an emission of radiation takes place, but every radiation which emit has a definite frequency. But in order to calculate the frequency, children, we must have the energy difference. There must be an energy difference between into those two orbits. So I have considered the energy in the higher energy orbit or state, that is N2. So at this state we have energy, and that energy can be calculated as E2. So energy acquired by the electron in the higher state is given by E2 and equals to minus. See children, I use the same formula, but instead of N I write on N2, minus M Z square e to the power 4 by 8 epsilon naught square H square, and instead of N I write on N2 square. Okay, this is the energy of an excited atom, okay, in the state? Higher state. This similarly, the energy in the lower state can be given by E1. So E1 can also written the same way, minus M Z square e to the power 4 by 8 epsilon naught square H square and N1 square. So these are the energy acquired by the electron in the two different states. Now I calculate the energy difference. Now I calculate the what difference? Energy difference. So energy difference is simply nothing but E2 minus what? E1. So E2 minus E1 now will be, E2 will be how much? Minus M Z square e to the power 4 by 8 epsilon naught square H square and N2 square. Minus this minus. Now E1 is already what? Minus sign. So I write down that minus, this minus sign. Now E1 is already minus sign. Now minus into minus will be what? Plus. So children, this will be plus. So I write down M Z square e to the power 4 by 8 epsilon naught square H square and N1 square. This is N2 square and this is N1 square. But I write this quantity as positive quantity first, and then I write on minus sign. So this is positive quantity, but in the expression you can see this is common and even this is common. So this quantity I will take common. So I write down M Z square e to the power 4 by 8 epsilon naught square H square bracket 1 by the N1 square I write down minus, then minus 1 by N2 square. So I just rearrange this, writing this quantity positive first and this negative, but taking the common. So I took common mz square into 4 by 8 epsilon naught h square. So look at the energy difference of electron in the two different orbits. So this is the energy difference. But we need to calculate the frequency of emitted radiation. And the frequency of emitted radiation, electromagnetic radiation, also called photon, is actually calculated by using Bohr's third postulates. Bohr's what? Third postulate, and Bohr's third postulate is also called Bohr's frequency condition. Bohr's quantization condition. We also call as what? Bohr's frequency condition, Bohr's frequency condition. Now Bohr's frequency condition can be measured from the which postulate? Third postulates. And according to Bohr's frequency condition, the frequency of the emitted radiation is always measured by nu, the symbol is nu, equals to E2 minus E1 by H. So children, we have already done in detail about this particular postulates called Bohr's third postulates. that measures the frequency of the emitted radiation. Okay, so frequency of emitted radiation equals to the energy difference of two electrons in two orbit divided by the constant called Planck's constant. Okay, now let me substitute the value. Now E2 minus E1, as you know, E2 minus E1 is nothing but mz square e to the power 4, okay, by 8 epsilon naught square h square with bracket 1 by n1 square minus 1 by what? N2 square. Whole divided by h. Whole divided by what? H. Now this h, this quantity will be reciprocal. If you reciprocal also, it will be m z square e to the power 4 by 8 epsilon naught square. H square into h, it will be h cube. Because when you reciprocal also, this h will be in the denominator only. That's why this h and h square multiply h cube. Bracket 1 by n1 square minus 1 by what? N2 square. So this is the frequency of the emitted radiation. So with this frequency, even we measure the wavelength. So we measure the wavelength of the emitted radiation. Now I write down therefore the wavelength. Okay, the wavelength of the emitted radiation. The wavelength of the what radiation? Emitted radiation, okay, is given by the relation, and the wavelength is measured by the formula. But there is a relation between frequency and wavelength. And children, you know frequency and wavelength are related by the relation. Speed of the photon or radiation equals to frequency into wavelength. See the speed of photon. Okay, nu is the frequency of the radiation, and lambda is the wavelength of emitted radiation. So C equals to nu into lambda. So from here what I do? I write down this way: 1 by lambda. I'll bring lambda in the denominator. 1 by lambda equals to nu by what? C. So the frequency, the wavelength of the emitted radiation can be given by this relation: 1 by lambda equals to nu by C. Now let me substitute the value now. Nu as the frequency is this much: m z square e to the power 4, okay, by 8 epsilon naught square h cube with 1 by n1 square minus 1 by what? N2 square. Okay, whole divided by C. Now this whole divided by C means this C and this denominator quantity will be multiplied. So it will be 1 by lambda equals to mz square e to the power 4 by 8 epsilon naught square ch cube. Okay, let me write it. This quantity will be multiplied. Even if you reciprocal, this C will be multiplied with denominator, with bracket 1 by n1 square minus 1 by n2 what? Square. Now this particular quantity, if you see in the expression of left hand side, is also called as wave number. This is also called what number? Wave number. Okay, this is also called what number? Wave number. Okay, now wave number means the number of wave per unit length. Wave number means the number of waves which can produce per unit length. Okay, now in this expression, if you see the quantity, this particular quantity, okay, the quantity m, okay, the quantity out here m e to the power 4 by 8 epsilon naught square ch cube. If you look at this quantity, other than this z, that means this quantity I am talking about, okay, is basically a constant. This quantity is basically what? Constant. And this constant is actually expressed by r, capital letter R, and this R is actually called as a Rydberg constant. So let me write down R equals to m e to the power 4 by 8 epsilon naught square ch cube. Now children, now for a given atom, mass is constant, charge of electron is also constant, permittivity is also constant, speed constant. Okay, but for different atom, your atomic number are also different. So the relation which I am going to write now, the wave number in terms of a constant, and that is for any of the atom. Okay, and this particular constant is actually called as Rydberg constant. So there is a constant name given out here that is called Rydberg constant. Okay, so from this relation of wave number, if I eliminate this m e to the power 4 by 8 epsilon naught square ch cube by this constant, then I write down it is 1 by lambda equals to C, 1 by lambda equals to, now I write down z square, this z square, and this whole quantity I am writing by r, bracket 1 by n1 square minus 1 by n2 square. So look at the expression of the formula that measure the wavelength of emitted radiation in terms of the atomic number of any of the atom of the element and Rydberg constant and the energy acquired by the electron in the different orbits. So this is Bohr's formula of hydrogen and hydrogen-like atom. That means this relation which I have derived, this is true for hydrogen and hydrogen-like atom. Hydrogen and hydrogen-like atom. Hydrogen-like atoms. See, I already told you what is hydrogen-like atoms. Hydrogen-like atom means basically like helium plus, He plus, lithium plus plus, okay, and basically hydrogen atom is H. So helium, He plus means this is a hydrogen-like atom because in this helium only one electron revolves around the nucleus. In this lithium only one electron revolves around the nucleus. Okay, and this hydrogen atom even has only one electron revolve around the nucleus. That means this is the general formula that we derive for measuring the wavelength of emitted radiation for any of the atom, hydrogen and hydrogen-like atom. Now we basically deal out here with the atom, and which atom? Hydrogen atom. And children, if you take hydrogen atom only, if you deal with hydrogen atom, remember this, what is the atomic number of hydrogen? 1. So if atomic number of hydrogen is 1, then I write the same formula, that is 1 by lambda equals to 1 square into R bracket 1 by N1 square minus 1 by what? N2 square. That means the wavelength of emitted radiation given by the formula 1 by lambda equals to Z square, but Z square I don't know is 1 square, which means 1 by lambda equals to R bracket 1 by R1 N1 square minus 1 by N2 square. Okay, so this is the formula. This is with what number? As I said, Rydberg. This is with what constant? Rydberg constant. Yes. So look at it. This is the correct relation that measures the wavelength of emitted radiation for hydrogen atom in constant in terms of Rydberg constant. 1 by lambda equals to R bracket 1 by N1 square minus 1 by N2 square. But out here R, the value can also be calculated. Now value of R, the Rydberg constant, as I said, is given by m e to the power 4 by 8 epsilon naught square Ch cube. This is Rydberg constant. So in this relation, if you see, mass of the electron is known. Basically, m is the mass of electron. Okay, mass of electron 9.1 into 10 minus 31 kg. E, the charge of electron, which is 1.6 into 10 minus 19 coulomb. Okay, C is the speed of the light of photon, that is 3 into 10 power 8 meter per second. H, as you know, Planck's constant, which is 6.6, okay, into 10 power minus 34 joule second. And epsilon naught is the permittivity of free space, and that is 8.85 into 10 minus 12 NO. So if I substitute this value in the relation and do calculation, children, remember that you will get the value approximately 1.097 into 10 to the power 7. 10 to the power 7. But the unit that we need to express, because the unit of R can be expressed from this relation. See, in the relation, see, these are simply the number on the right hand side. But lambda has a unit. And you know what is the unit of wavelength? Meter. So if meter is in the denominator, and if I take in the numerator, then it is per meter. So remember, the unit of R is per meter, taking meter from denominator to meter, numerator. So Rydberg constant is basically approximately how much? 1.097 into 10 power 7 per meter. So this is the value that we take. Okay. Now we have derived the expression of frequency and the wavelength of emitted radiation. Now in the next YouTube video, we do continue with the expression of energy of an electron, okay, in any of the orbit in constant, what constant? Rydberg constant also.